Hi, good morning, everybody. Thank you for coming out on such a young morning. And hopefully the rain won't go too long. Looks like when I came in here, it was slowing down already. Hi, important announcement. Only 10 more shopping days till Halloween. Good news is, I already got my Halloween candy yesterday, or the other day, I take it back. And don't forget, come to Wednesday before Halloween. Let's check something real quick. Yeah, the Wednesday before, come in costume like you all are now. You all look like students. And I bring candy, which is sort of dumb because you'll all be on the sugar high in my class. But I celebrate Halloween. And the candy I bring is not the cheap stuff, the stuff I like. You're going to somebody's house and they have stuff you would never buy. When I was a kid, well, come on. All right, we're talking about gases. Last week, I talked about PV equal nRT, the ideal gas law. Remember, PV equal nRT tells you when to check your tires. In winter, temperature goes down, pressure goes down. In summer, pressure goes up when the temperature goes up. So don't forget PV equal nRT. Now, as I mentioned earlier, the gas laws have evolved because of the Industrial Revolution and the interest and the importance of understanding gases under various situations because of the steam engine and then later the combustion or gas engine. And one important one, oh, by the way, it's a simple one, so you can smile. You don't have to. And that is Dalton's law of partial pressure. And Dalton's law of partial pressures is the total pressure exerted by a mixture is the sum of the partial pressures of the individual gases. I will never ask on the test to describe what's Dalton's law of partial pressure, but I will ask you to know how to use it. And partial pressures, what is a partial pressure? Hold on 1 second, I fixed it. All right, a partial pressure is the pressure that a gas in a mixture would exert if it were alone under the same conditions. Now, the important part of Dalton's law is the total pressure equals the sum of the partial pressures. P1 is the partial pressure of one gas, P2 is the partial pressure of another, and so on. You have 10, you'd have 10, P1 through P10. And the total is the partial pressure sum of each individual gas if it were alone. And that's Dalton's law of partial pressures. let's look at a Dalton's law problem. And if a tank, assume a gas tank, contains oxygen at a partial pressure of 751 torr and carbon dioxide at a partial pressure of 101 torr, then what is the total pressure of the tank? And as I've taught you all semester, first thing to do is figure out what are you being asked to find. And what you're being asked to find is the total pressure. What are you given? You're given the partial pressure of oxygen equals 751 torr. And the partial pressure of carbon dioxide is 101. And once you look at this, immediately you should think of Dalton's law of partial pressure. In this case, the total pressure equals the sum of the partial pressure. In this case, that's PO2 plus P partial pressure CO2. Say that 3 times quickly. And now, what do? We put in the numbers. And hopefully I added them correctly. If not, one of you let me know. Remember, addition, you get the same number of significant figures in your answer as the number that has the lowest significant figures, 0, 0. So my answer has 0 significant figures. And that's Dalton's law of partial pressure. It's not that complex, but it was quite important because when a number of these laws were proposed, nobody knew about this. And that's the importance of these things. Now you look at it and say, well, that's common sense. By the way, did I tell you the greatest of all mentors I ever had, one of the 2 greatest, Sid Shapiro, used to always tell me, you know, common sense is not common. He was right. All right, let's do another one. Why don't you try this one on your own? Question.
Why do we find Pn?
Well, Pn is just a mathematical expression. Pn is a way of saying if you had 10, n would be 10, so it'd be 1 plus 2 plus 3. If it was 2 of them, then I'd only put P1 plus P2. So this is a way of showing it. Another way, which I didn't want to confuse you, would be, for those of you who know math, if you're familiar with the sum set, most of you are not, so that's why I didn't put it, and I put it like that. So if you have 5 gases, you have P1, 2, 3, and the end tells you also have P4 plus P5. Okay? And now you know the secret of Pn. All right, why don't you try this one and I'll decode it for you so you can read my handwriting if you can. If a tank contains nitrogen gas or nitrogen at partial pressure of 441 torr and argon at a partial pressure of 42 torr, then what is the total pressure of the tank? How fun. First find out what are you being asked to find, and then what are you given, and then I'll help you out. By the way, don't forget a commercial from Dr. White. If you missed something or you'd like to see it again, check out my YouTube channel for Chem 1105, and you'll see here I am. And I'm pretty much up to date. I have a few older ones I still have to get up there. But hopefully today's lecture should be online by Tuesday afternoon, Tuesday evening. All right, let's take a look at this. First of all, what are you being asked to find? What's the total pressure of the tank? What are you given? You're given the total partial pressure of nitrogen equals 441 torr. And we have partial pressure of argon equals 42 torr. And now when we look at this total pressure, partial pressure, it gives it away. Dalton's law of partial pressures, which is the sum of the partial pressures equals the total pressure. So in this case, I have P total equals partial pressure of nitrogen plus partial pressure of argon. And now, since I took the time to figure it out, I can just fill in the stuff. And this one is 441 torr plus 42 torr equals 483 torr, if I did my math correctly. And there you go. Oh, let's do one more. These are fun. All right, let's take a look at another one. A gas tank has a total pressure 851 torr. That's better. And it contains nitrogen at a partial pressure of 551 torr and oxygen gas. What is the partial pressure of the oxygen gas? I'll let you try this one on your own, because I like to share, and then I'll do it. Those who finish early, try doing this. One forward, one back. When you master that, do it with your thumbs. All right, looks like last number is this one down. And how do we do this? Well, let's find out, what are we being asked to find? Partial pressure of oxygen. What are we given? P total equals 851 torr. And the other gas besides oxygen, P nitrogen, is equal to 551 torr. So, what do we do? We're trying to find this, and now we're looking at total pressure, partial pressures. Immediately, I think of Dalton's law of partial pressures. And now we have this. The total pressure of the tank is equal to the partial pressure of nitrogen and oxygen. Now, what are we being asked to find? The partial pressure of oxygen. Now, I haven't done this before, but I have a suspicion you know how to do this, so let's find out. When you have an addition, how do I get a variable on one side alone? It's not a division or multiplication. Well, if I subtract P sub N2, or partial pressure of nitrogen, anything minus itself equals 0, and 0 plus something equals that something. So on this side, to get rid of this, I will do the following. Well, whatever you do to one side, you have to do to the other. And now this minus this is 0, so I'm left with PO2 equals P total minus the partial pressure of nitrogen. Dr. White likes to flip it around, so I'm going to. Good habits I don't break. And this is equal to P total minus the partial pressure of nitrogen. And I took the time to figure that out. That's 851 torr minus, okay, ahead of myself here, minus 551 torr. And if I did my math correctly, that's 300 torr. And that's how you do it. And that's Dalton's law of partial pressure. It's easier than PV equal nRT, but it's still important. Any questions? All right. I don't know if I told you a secret, but if you look right down here, I'm on page 28 of 28 pages, or slides, which means I'm done with this chapter, which also means this Friday in lab, I will go through the gas problems for this chapter. I highly recommend you try them before I go through a couple in class. And you know what else it means? It means new chapter time. Now, so far I talked about gases. What's another state of matter that's important in chemistry? And that's liquids. And so let's move on to liquids. And when we talk about liquids, the important thing is solutions. All of you have used solutions all of your life. You may not have realized it. And this deals mainly with liquids, but other things too. So the question is, what's a solution? Well, one way of saying it is a solution is a mixture when one substance is uniformly dispersed in another substance. Another way of saying that is it's a homogeneous, that means it's the same throughout, combination of two or more substances in which each substance retains its own chemical identity. That means if you mix two things together, it's homogeneous, but they don't react, because you don't want them to. So this is a solution. Don't forget, everything on the screen is available on Blackboard. And tonight at midnight, I'll be giving speed note-taking lessons. Boy, the view is the same from this side as that side. Everybody just about caught up? I'll walk slowly over here, give you a chance to catch up. Okay, let's continue. Now, I haven't done this in a while, so I better. Oh, it's Subtle Monday. All right, when we talk about solutions, there are two key terms you should know. One is the solvent. The solvent is the component present in the greatest amount in the solution. That's the first definition you should know. Oh, it even says it on the board. And the second definition you should know when we talk about solutions is solute. And solute is a solution component that is present in small amounts relative to the solvent. Therefore, when we talk about solutions, you have a solvent. That's the component present in the greatest amount. And the other components that are present in the smaller amounts are called solutes. And let's take a look at the following. A solution contains 80 grams of water and 20 grams of sugar. I think I got Halloween on my mind already. And what is the solvent and the solute of this solution? So how do we determine that? Well, the solvent is the component present in the greatest amount. And now you have to use your knowledge of numbers, and I hope you all agree 80 is larger than 20, and therefore the solvent of the solution water. And everything else are solutes. There's only one. And therefore, that's important knowledge to have. Now, in our world, water is probably one of the most important solvents, but it doesn't have to be the only solvent. There are others. In a solution, if you follow the definition strictly, which I tend to do, there's only one solvent in a solution, but there can be many solutes. Let's do another one like this. All right, let's take a look at another one. And here, a solution contains 70 grams of isopropyl alcohol, it's a compound, and 30 grams of water, which is another compound. And what is the solvent and what is the solute of this solution? And for that, I'm going to share and let you try this. That looks like everybody's done. Let's take a look at this. What are we being asked to find? What's the solvent and what's the solute of this solution? What's the definition of a solvent? The component of the solution that's present in the greatest amount. And notice we have 70 grams of isopropyl alcohol, 30 grams of water. I hope you all agree that 70 is greater than 30. And therefore, the solvent is isopropyl alcohol, and the solute, which is normally not the case, but in this case it is water. Now, why did I pick this mixture? How many of you are familiar with a product you can buy in many places called rubbing alcohol? And rubbing alcohol, I guess you can rub it on yourself. It's a disinfectant. It's used for other things too, which I'm not aware of, but that's an important thing. And if you go to your local big box store, supermarket, or anywhere else they sell rubbing alcohol, you'll find it's 70% or 70 parts of isopropyl alcohol, 30 parts of water. A couple of years ago, they also started selling 90 parts isopropyl alcohol and 10 parts water, and it's still the same. If you look at the bottle, it's homogeneous, the same throughout. Now, quick little, do I have time? Oh, I do. Dr. White's story. When I was younger, for a long time, until they came out with the electronic thermometers, if you went to the doctor's office, I can remember when I was a kid, I hated this. First thing they do when you go into the examining room, the nurse comes in and says, here, let me take your temperature. And they had a thermometer. Back then it was mercury in glass ones. And it was in this container that had a liquid in it. The nurse would take it out, take some cotton, wipe it off, and stick it under your tongue, and it tasted, I mean, really, yeah. And that's because in the container they had isopropyl alcohol, water, rubbing alcohol. So the last person who used the thermometer, they had germs on there. It killed them, and that way you won't catch whatever they had. But it still tasted awful. Why they didn't rinse it with water too was always a mystery to me. And that's rubbing alcohol. Now, when we talk about gases, not gases, solutions, there are different types of solutions. Most of the time, I will think of solutions being a liquid. But you can have solutions that are gas, you can have solutions, like I said, that are liquid, and you can even have solid solutions. Now, most of you probably never thought of it, but right now, you're sitting in a solution. What? Yes, the air. The air is a mixture of nitrogen and oxygen. It's homogeneous, and let me prove it's homogeneous. Everybody watch. Right now, I'm breathing. Everything's okay. If I go over here, I'm not going to say, I can't breathe, there's no oxygen. Yes, there's the same amount, because in this room, the air is homogeneous, which is a good thing. That means when you're walking around here or outside, all of a sudden you won't stop getting oxygen, and you pass out and die. So, another component in the air is the water vapor, moisture. And that's all part of air is a very complex solution, but mainly oxygen and nitrogen gases. Now liquid, I think you've all had tea, which I had my mug this morning, and that's the solution. If you look at, by the way, I think I mentioned it, but I'll mention it again, being from Chicagoland, the stuff in a bottle that's carbonated or canned, non-alcoholic, we call pop. And pop is a very complex solution. Look at the label. You'll see it's got water, sugar, different flavorings, and carbon dioxide. So it's a mixture of both solids, liquids, and gas all together. Now, if you were to take and put some salt in here, shake it up, dissolve it, that would be a solution. And if you were to do a better one, which would be put some sugar in here, that would be a solution. Ooh, I just thought of one I haven't thought of in years. And that is, when's the last time you had some Kool-Aid? When I was a kid, that was real big. And Kool-Aid, when you make it, is a solution. It's water, it's sugar, because they tell you to put in about 10 cups of sugar, and then you have the little envelope that you pour in there, and you make your Kool-Aid. And then the guy comes through the wall in the picture and everything with a smile on his face. That's the solution. And I just thought of another one, which I haven't seen advertised. How many of you seen the commercial where they sell the little flavorings you put in a bottle? And it's always a cute commercial because you see this color stuff start dispersing in the liquid. I enjoy that, I'm a chemist. And there you're making a solution too. I don't know, do you also put 5 cups of sugar in that too? And what's some other solutions? For those of you who like champagne, that's a solution. Hard liquor is a solution of ethanol, alcohol, and water. And one you probably don't think of, but the next time, oh, did I tell you that when you walk out that door, you can think about chemistry and it won't hurt? And so next time you pass a gas station, the stuff they're selling, gasoline, is a very, very complex solution or mixture of very many different components. And I've worked in that industry, or actually the companies I worked for, one in particular, made additives. How many of you have been in a Shell station and seen where it now contains nitrogen They've been doing that for a number of years. Well, a long time ago, when they first figured out they needed this additive, it's not nitrogen atom or gas, it's a molecule called an amine oxide. I was working for a company, and Shell came to our company because we were one of the biggest producers of the molecule they needed. And I was the section head of process and product development, which meant I worked heavily with the plant to bring in new products. And I went to a meeting with the VP, our vice president of marketing and sales, and said, we just got this great order from Shell. What? Well, in 8 weeks, they want 5 million pounds of this compound. And I looked at him, the production manager looked at me and said, what? We need to get it, because they were going to do a national rollout of what they call the nitrogen additive, which you now see in their commercials. By the way, that is a good additive. It helps clean, one of the things, the carburetor tips of your car, so it runs nicely. And so I had a few days of not too much sleep, and same thing with the production manager. We worked hard, set up a campaign where we made those 5 million pounds and shipped it. That was an amazing feat by us to do. But anyways, gasoline is a very complex mixture. Did I tell you about the different grades of gasoline in here yet? And this won't be on a test, but think of this as a public service from Dr. White. If you go to a pump, you'll see 3 different gas station pumps. You'll see 3 different grades, whatever they call them, regular, whatever they call the medium and the premium. What's the difference? Well, having worked with Shell and also other companies to make additives that they put in there from the company I worked for, I learned a lot about gasoline. And the most expensive has the best and most amount of additives. The low regular has the least amount. Now, what I do is, most of the time regular is fine unless you've got a Ferrari or a Lamborghini, which I don't, at least this week, maybe next week, but not today. But about once every 3 months, I'll let my tank, which normally I don't like letting go below half, this is my personal preference, I'll take it down to about 3/4 empty, 1/4 full. I never let that get to empty ever. But anyways, then I'll go into Shell, and Shell's the best gas around. I don't get any kickbacks from them. I wish I did, but I don't. And fill up the tank. And I do that about once every 3 or 4 months, and that keeps your engine nice and clean and running well. And even though it's a little extra money, think of it as once in a while you put stuff in there to clean out your engine. And it works. Did I tell you the best and worst gas? Best gas is Shell, and has been for decades. It's just the best. Right behind it, not far, is Mobil. Now, and then the worst gas is BP, or used to be Standard. How bad is it? Well, they've been bad for many decades, but if you go back to the newspaper, and you can do this on Google, here in Illinois and northern Indiana by Gary, that whole area, BP made the worst gas ever. I don't know what they messed up, and destroyed about 3,000 car engines. People put their gas in and destroyed their engine. Well, no way am I going to use gas from a company who can't guarantee the quality of their product. It's called quality control, and I worked with that, and they should be able to do it if they don't. All right, moving on. Other items that you might want to consider: solids. Brass is a mixture. Stainless steel is a mixture. Some of your dental fillings, now they use mainly polymers, but they used to have amalgam of metal that I have still, and because I had cavities long ago, and those are mixtures of metals that are become a solid. And one of the things in amalgam has been mercury. And people have said, well, it's bad for your health and everything. Well, I'm still alive. Anyways, I know people, my dentist told me about one dentist, they came in and had all their fillings removed and replaced. And the dentist said, you don't have to, but the people are adamant, so he did it. But mercury is something to be careful. Now, probably the most important solvent in our planet, in our world, is water. And water is called a polar solvent. I'll talk about that later, what is polar, and it's due to polar bonds. Now, this is one of the most important things about water or chemistry I'll teach you this semester. Water molecule, line is a pair of electrons. I'm not showing the non-bonding electrons. Water molecule again, water in stereo, and no, you're not seeing double. Now, a long time ago I mentioned, and said you didn't have to know it for a test, but it's important to understand now, when you have atoms with different electronegativities, that means the power they have to bring electrons toward themselves, something interesting happens. Now, wait until everybody's through copying this down. Look on Amazon, see if they have any speed writing pencils or pens for you people. No. All right. I'll come back to the slide in case you haven't finished it. Let's go to my favorite periodic table. One of these days I got to find out who did this and email them and thank them. All right, periodic table. One of the things I mentioned earlier in the semester, when you go from this side to that side, elements have stronger electronegativities. Electronegativity is a measure of how strong an atom or element is when they're sharing electrons. And going from here to here, you become more electronegative, or the elements are stronger, I like that, stronger, for pulling electrons. Now, if you look over on the left, you have, weak little hydrogen, and over here you have strong oxygen. So what that means is they're sharing electrons, but oxygen says, hey, I'm stronger than you, let's share them, but let's share them a little closer to me. And because of that, there's a slight negative charge on oxygen and a slight positive charge on hydrogen. And the same thing here. In math and chemistry, this is the Greek letter delta, which means difference. That's a capital delta. Lowercase delta is this, and that means slight or little difference, and that's why we use that. Now, the same thing happens to this molecule of water. There's a slight charge because of the difference in electronegativities. With the rain today, it reminded me of a memory in the past. When I was very young, my older sister is 7 years older than I am. We were out in a rainstorm with one umbrella, which we shared, but she was bigger than me. She shared it closer to her, even though it sort of covered me, but more her. Same thing with, don't tell her I said that, I told that story. But anyways, because of this, there's a very tiny little charge on oxygen, and the same thing on hydrogen. Now, how many of you have heard the term opposites attract? nature people. You see, my best friend and his wife, you wonder how they've been married all these decades, because they're total opposites, but it works. And there's a slight attraction, we call that electrical, or more specifically, Coulombic attraction, that the oxygen from one molecule water slightly attracts the hydrogen from another molecule because of opposite charge. And we call this attraction a hydrogen bond. It's not a true chemical bond. It's a very tiny force, but it's a very important force. And that's a hydrogen bonding. Now, it turns out anytime you have a molecule that has hydrogen atom on either nitrogen, oxygen, or fluorine, it can form hydrogen bonds. And water can hydrogen bond to itself and other molecules. Now, the important thing about hydrogen bonding is this. Wait a second, that's water. What's so important? Everybody see what state of matter this material is? It's a liquid. And why is it a liquid? Because of hydrogen bonding. At this temperature the room is under, for our daily life, other molecules with the same molecular weight that can't hydrogen bond are gases. Water is not. And why? Because of hydrogen bonding. These hold the molecules together with a slight force that makes it a liquid at this temperature. Just think what our planet would be like if water at this temperature was a gas. Well, we wouldn't evolve the way we are this way, because think about it. In my veins, yep, they're still there, on the side too, you have blood. Blood is made up mainly of water. If it was a gas, we wouldn't exist the way we are today, because our veins, I don't think, are designed to carry gas. And other molecules can hydrogen bond. Alcohols are molecules in organic chemistry. We show an alcohol like this, where R is something with carbons that will not be on the test. And same thing happens like this. True story. Do not go into a bar and tell a bartender, you know why you can make mixed drinks? Because alcohol and water both can hydrogen bond. Bartenders don't like to be taught chemistry. True story. Anyways, alcohol is one of those, and other molecules too. How many of you are familiar with the term RNA and DNA? And how many of you are familiar with the shape as a double helix? And that's mainly because one of the important reasons, hydrogen bonding onto nitrogen with a hydrogen in the proteins, which are amino acids that make up your RNA and DNA. So if you wonder, why am I learning this stuff? Well, think about your RNA and DNA and your amino acids and proteins. All right, switches off. Let's just talk about something important, but I won't put this on the test. Don't fall asleep, please. All right, and now let's talk about hydration. And if you take this bottle of water, and if I were to put some salt in there, sodium chloride or sugar, and I go like this, lo and behold, the solids disappear. And what has happened? Hydration. It becomes soluble. And how does that happen? The forces that hold the solid together are broken, and each molecule of the solid is now surrounded by water molecules, and we call that hydration. Now, one of the more important things for your everyday life that I can teach you this semester is the following. and that is like dissolves like. And like dissolves like is an important principle. And what is it? Like solutes are soluble in like solvents. Polar solvents are soluble in polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. And what this also implies, but I don't have it on the slide, is if you mix polar and nonpolar together, they're not soluble because of like dissolve like. Now, when we look at substances you use in your daily life, the most polar thing we can use is water. Now, another polar substance that you use on a daily life basis, salts. Most salts are polar. Now, this is a rule of thumb, not a law. That means there are exceptions, but as it's written on this, no, it's on this thing, it works about 95% or more of the time. What's another one? Well, I talked about alcohols. And sugars like table salt, sucrose, table sugar, sucrose are soluble. Now, are polar. What's non-polar? Gasoline is non-polar. If you mix gasoline and water together, don't try this home, please, it will separate, just like oil vinaigrette dressing. And how many of you have ever, this would be a good day to look around, go into a gas station after it rains, and then the sun comes out, and you see little puddles, and on top of the puddle you see a rainbow. And wow, what's that? Well, the gasoline that was on the surface by the gas pumps, which people, if you've ever noticed, sometimes spill onto the surface by the gas pumps. You have water. Gasoline is not soluble. Why? Because gasoline is non-polar, water is polar. Like dissolved like says they have to be the same. They're not. So the gasoline sits on the top in a thin film. When the light comes down from the sun, it refracts it and makes the rainbow, which I always find enjoyable to look at. All right, what's another example? Vegetable oil is non-polar, whether it's corn oil, soybean oil, or just plain old vegetable oil. How many of you are familiar with Italian dressing or oil vinaigrette dressing? And if you make your own or you go to the store and you buy it in the bottle, what do? You shake it up and put it on your salad. And then if you put the bottle down after a couple minutes, what happens? It separates. Why? Like dissolves like. The vinegar, oil vinaigrette, vinegar is a mixture of mainly water with a compound we call acetic acid. And the other part, the oil, is either vegetable oil or if you make your own with olive oil, same thing. And because of like dissolves like, it doesn't happen. What are some other things that are non-polar? Vaseline, which is also known as petroleum jelly, is non-polar. Baby oil is non-polar. And why do they use it on babies? To keep moisture away from the surfaces of parts of their body that get wet or humid. Because it's non-polar. Because like dissolves like, this will not allow water to get through it. How many of you have ever put gasoline on something and water doesn't take it off that easily? Like dissolves like. Oh, quick thing about baby oil, safety thing. When I was teaching organic a number of years ago. I had in my class a woman who was going back to get her master's in nursing, and she needed to take organic. And we were talking about baby oil, which I taught in that class too, and she had been a it was at that point still, neonatal nurse and natal nurse, which means she worked in emergency rooms and other places with babies. One of the things they always warn new parents is baby oil and Vaseline are very flammable, almost as flammable as gasoline, not quite. Therefore, don't ever have lit candles around if you're using baby oil, or I don't know why now, but back then some people might have smoke or any kind of flame source, because that will start a fire. Now, they're flammable, and I just thought I'd let you know that. But anyways, a number of years ago when I taught Chem 1211 here, I had a very interesting and nice, smart student in my class, and I put this up on the board and talked about light dissolves light. Things that are polar are soluble in polar things, things that are nonpolar are soluble in nonpolar things. And the student raised his hand and asked me, well, if that's true, if I take vegetable oil and Vaseline, will I get a homogeneous soluble solution? And I looked at the student and said, probably, but I've never done it. Next lab we have, I'll give you a beaker, get some vegetable oil, some Vaseline, and you mix them together. And lo and behold, the next lab, the student did that, and it was soluble. Why you'd want to do that, I have no idea, but light dissolves light work. Now, if you look at the very bottom, and I don't teach it in this class, dirt and grease are nonpolar. That's why if you have dirty hands or dirty clothes, and you just go water, it doesn't work. And what do you use? Soap. And soap is a special thing that has both polar and nonpolar part, and we call that a surfactant. And the next time you wash your hands, you're doing chemistry, organic chemistry, and because light dissolves light, the soap helps make the nonpolar dirt and grease acceptable to water, and I won't go into that. Oh, wait, I take it back. For 1105, I'll talk about that later in the semester. All right, let's take a look at the following. Dr. White got creative. Compound A, that's pretty creative. Compound A is soluble in water, but not in vegetable oil. Compound B is soluble in vegetable oil, but not in water. And the question is, what are the polarities of A and B? And the dreaded part of the question, how do you know this? Well, I could have also said, please explain. So why don't you think about this? Remember, light dissolves light. change the clock. I just started clocking. Can't you see?
Show me what the P word is, the third line from the bottom.
I'll read this again, okay? Compound A is soluble in water, but not in vegetable oil, okay? Compound B is soluble in vegetable oil. It's soluble, and I spelled it right. I tell you, I was always the first one down in spelling bee, always. All right, but not in water. What are the polarities of A and B, and how do you know it? Is that better? Remember, it's always true in my class or anywhere around me. There's no such thing as double question. So, a good question is, what'd you write on the board? I can't read it. All right, let's do this. Now, if we look at this, what do you know? You're using water and vegetable oil. Water is polar, vegetable oil is nonpolar. As soon as you see a substance is soluble in water, you know it's polar. And to confirm that, it's not soluble in vegetable oil, which is nonpolar, so like dissolves like works. So, what do we know? We know compound A is polar. Next, compound B. Compound B is soluble in vegetable oil, which is nonpolar. It's not soluble in water, which confirms it's nonpolar. And therefore, compound B and how do I know this? I'm running out of room here because of the monitor, so I'll put it up here. You know that because like dissolves like. And that's how you use like dissolves like. Now, one quick public service announcement, or not announcement, commercial from Dr. White. You see on TV those public service commercials to help you out and things like that. He moved out of the area, but I used to have a friend, and when he'd come over to my house and park in my driveway, his car leaked oil. Oil is nonpolar. And when he'd leave, I'd have the stain on my garage, on my driveway, which looked unsightly. But being an organic chemist, knowing like dissolves like, water is going to take that out because motor oil is nonpolar also. And therefore, what do you use? Soap and water, and it pulls it right out. What do I find for that? How many of you are familiar with, and I don't get a kickback from this company, but Dawn dishwashing liquid, that's the best out there, my personal opinion. And I went out there, and I'd take the bottle, a little bucket of water and a sponge, and I'd pour some Dawn, a little bit of water, more Dawn, rub it in there, wait about 2-3 minutes, and then take the sponge and pull the oil spot right off, and I'd be happy. And then, never, because he was a good friend, why don't you get your car fixed? Or park on the street. All right, let's continue on. Switch is off on this slide. I think you've heard of electrolytes. question. Different.
How do you know if something's polar and not polar?
Well, one way is, good question, dissolve it and see if it dissolves. By definition, water is polar. Most things, remember, it's a rule of thumb, not a law. If it dissolves in water, it's polar. If it doesn't, it most likely is not polar. And that's the quick way. I will never ask you something like that. The ones you should know from that list, water, salts, sugars, those are things you use in your daily life, maybe alcohol, but I'm not going to rub it in. Ooh, that was bad fun. Look out, I'm in true form this morning. And from here, non-polar gasoline, vegetable oil, and maybe Vaseline baby oil. And that would be that. All right, now let's talk about electrolytes. Switches off. When you put a salt into water, it gets hydrated, and because it's an ionic bond, it separates into its ions. If you put sodium chloride into the water, you'll have, once it's dissolved, sodium plus, chloride minus ions. And we call those electrolytes. Pure water, which you can't get in your daily life, I can, but you can, does not conduct electricity because there are no electrolytes. You can't get it in the water from your tap or anywhere else you buy water. It has a small amount of ions. That's why you never want to get electricity into water you're standing in, because it will kill you. But we call these electrolytes because they conduct electricity. They help water conduct it. Now, unfortunately, I learned about the bad thing about electrolytes a number of years ago. It happened a number of times. There were a number of radio stations throughout the country over a certain period that had these awful contests, and the contest was to win a large sum of money or a car, the person who could drink the most water in a certain amount of time would win. And these people are drinking gallons of water. Well, when that does that and your body gets rid of it, it flushes out your electrolytes from your body, which kills you. And unfortunately, a number of people who were enough that they stopped doing it, who won the contest within a day or less, died. Now, other better story is, if you ever work in a plant, especially a chemical plant in a hot area, like in Alabama, even in Illinois, if you go in the plant in the break rooms, they'll have on the wall a dispenser of salt tablets. Salt tablets? Why? Because if you're sweating a lot, your moisture, women perspire, men sweat, and your moisture, sweat, not moisture, your sweat or perspiration contains salt electrolytes. And if you are in a hot environment, perspiring or sweating, depending on your sex, you're losing a lot of salt. And they have salt tablets so you can replenish your electrolytes. Excuse me, I'm getting all choked up over it. Sorry, yeah, with some electrolytes. That's better. And if you look at a bottle of Gatorade, it's chock full of different salts or electrolytes. I guess I'm allergic to electrolytes. Now, switch still off, things that don't help conduct electricity are called non-electrolytes. Example, that would be sugar. Where's the cough medicine? Sugar is an example of that. All right, let's talk about solubility. An important thing, switches on, solubility. And solubility describes the amount of solute that can dissolve in a given amount of solvent. And this is a very important concept and value. I got it. And so if we look at solubility, the solubility of a solute is the maximum amount of solute that will dissolve in a given amount of solvent. You can't put one molecule more, switch is still on, in that solution. If you do, it will precipitate out, it won't dissolve. So solubility of a solute is the maximum amount that will dissolve in the given solvent. Never been home without them. So let's go out into the real world. And when we talk about solubilities of a solute, the nice things about Wikipedia is it's so heavily policed in chemistry by people like myself. I trust numbers I see here. And if you look up sodium chloride in Wikipedia, look on the right, scroll down, you'll see right here properties. And you see solubility in water. And notice here they tell you it's probably at room temperature, that's why it's got the 1 here. And the reference, you can put up to 360 grams of sodium chloride per liter of water and dissolve it. With that, I'm going to let you go or you'll dissolve it. And with that, I'll see you on Wednesday. Don't forget Friday, I will be going through the gas law.